Can you give me the permissions to share the screen?
Sure. You can share the screen now, sir.
Okay. Good morning, students. We will wait 2 minutes to join the rest of the students. Okay, we'll start. Right. hydraulic lifts works on the basis, hydraulic lift works on the basis of Pascal's law. The increased pressure will be enhanced for the larger area of cross section. Let us suppose this is one piston of smaller area of cross section. And this is the another piston of larger area of cross section. This is the small area of cross section A1, and this is the larger area of cross section A2. So in the servicing stations, here they'll keep on the platform, they'll keep the vehicle. They'll keep the vehicle on the platform. And by changing the pressure at the first cross-sectional area, here they'll apply the pressure. And the pressure will be enhanced for the larger area of cross-section. Here, cross-sectional area of the piston is there. So whenever the pressure is increased at the first cross-sectional area, that will be enhanced for the larger area of cross-section. It will be enhanced for the larger area of cross-section. So then by changing the pressure here, we can change the pressure in the larger area of cross-section. So enhanced means the applied pressure will be enhanced for the larger area of cross-section. That's called Pascal's law. These hydraulic lifts, they work, hydraulic brakes, they work on the principle of the Pascal's law. That means in the master cylinder, master piston will be there. Applied pressure will be enhanced through it, and that will be applied for the larger area of cross-section. An ideal fluid flows through a pipe of circular cross-sectional area with diameter 5 centimeters and 10 centimeters as shown. The ratio of the velocities of the fluids at A and at B. Larger area of cross-section and smaller area of cross-section, these are there. This is the pipe of different area of cross-sections. This is the first area of cross-section. This is the second area of cross-section. In this radius I am taking, they have given diameters. Diameters and radius, they are proportional. This is the diameter or the radius I am taking, art. The velocity at the first end is taken as a V1, that is a ratio he has asked V1, and the velocity at this second cross-section area is taken as a V2. V1, V2 are the velocities at the first cross-section area and at the second cross-section area of cross-sections. Now, what did they ask? Equation of continuity, whenever we take, according to equation of continuity, A1 V1 is equal to A2 V2. Otherwise, we may take A into V is taken as constant. A into V is taken as a constant. That pi r square into V is taken as a constant. Pi r square into V is taken as constant. Then V is inversely proportional to r square, we write. If we send it to right side, and the pi is constant. So V is inversely proportional to r square. From this we will write V1 divided by V2 is equal to R2 divided by R1 whole square, R2 by R1 whole square. So V1 divided by V2 is equal to R2 is given as 10 centimeters. 10 divided by 5. R1 is 5 centimeters. R2 is 10 centimeters. R1 is 5 centimeters. 10 by 5 whole square. There, 10 that cancel in 2 that cancel in 10. 5 that cancel in 10 two times. Therefore, V1 divided by V2 is equal to 2 whole square, means what? 4 by 1. So therefore, the ratio of velocities will be 4:1. Right? Next problem. A flow of liquid is streamlined if the Reynolds number is. Reynolds number, if it is below 1000 or less than 1000, that is called as streamline flow. If the Reynolds number is in between 1000 and 2000, that is the uneven flow. If the Reynolds number is greater than the 2000 and 2000 to 3000, that is called as the turbulent flow. If the Reynolds number is in less than 1000, that is called as the streamline flow. For that, streamline flow will say that. Reynolds number, if it is less than 1000, we'll say that it is a streamline flow. Next, capillary. Two capillary tubes of different diameters are dipped in water. The rise of water is, there is a rise of water. Surface tension 2t cos theta is equal to 2t cos theta is equal to RHDZ. 2t cos theta is equal to RHDZ. Therefore, H is equal to 2t cos theta divided by RDG. D for density, R is the radius, T is the surface tension, G is acceleration due to gravity. Height is the liquid that is raised in the capillary tube. Let us suppose whenever a capillary tube is taken, means just like a straw. If you dip the straw in a juice glass, what happens? Rise of the juice will be there in the straw. Rise will be there in the straw. Let us suppose this is a straw. Rise of liquid will be there in the straw, right? The rise of the liquid that depends upon the diameter of the straw. Like instead of capillary tube, in our general language, I am saying that straw. Okay, depends upon the size of the diameter of the capillary tube, rise of liquid will be there. How? Height that rises in the capillary tube, height of the liquid that rises in the capillary tube, that depends upon the diameter of the capillary tube or radius of the capillary tube. Then H is inversely proportional to R, means if radius is more, height raised is less. If radius is less, height of the liquid raised will be more. Similarly, diameter of the capillary tube, if it is more, height raised will be less. If diameter of the capillary tube is more, height raised by less. And if the diameter of the capillary tube is less, it rises more height. The liquid that rises more height. See, we'll check that options. First one, same both in the tubes, wrong. Greater in the tube of larger diameter, wrong. So greater in the tube of the smaller diameter. If the diameter of the pipe is more, then it is less. So smaller diameter, if it is there, greater rise of the liquid will be there. For the smaller diameter of the pipe, greater rise of the liquid will be there. 8 drops of 8 water drops are falling through air with the steady velocity 10 centimeters per second. If the drops combine to form a single drop in size, then the terminal velocity of the big drop is. First, we'll take what is the given data. 8 drops are there. A single drop, it is a single drop of radius capillary is there. It splits into 8 identical drops. 8 drops of the radius. 1, 2, 3, 7. 8 drops of each radius is taken as a radius of the each one is taken as a small r. Small r is the radius of the each drop. Then first of all, we have to take the relation between the capital R and the small r. This is whenever we take that volume of the big drop is equal to volume of the n drops. Volume of all n drops. Volume of the big drop will be equal to volume of all n drops. Then volume of the big drop will be equal to 4 by 3rd pi r cube. 4 by 3rd pi r cube. This is the volume of the big drop. N into volume of the small drop will be 4 by 3rd pi into small r cube. Both sides we can cancel 4 by 3rd pi, 4 by 3rd pi. What is there? Capital R. It is a capital R. Capital R cube is equal to n into small r cube. If you send this r cube to right side, r is equal to n power 1 by 3 into r. Capital R is equal to n power 1 by 3 into small r. This is the relation between the capital R and small r. Then what we have to prove, if the terminal velocity is to for the big drop is to be calculated. What is the velocity expression for the terminal velocity? Terminal velocity Vt is equal to Vt is equal to 2 by 9 r square g divided by eta into rho minus sigma. R square g divided by eta into rho minus sigma, right? Then terminal velocity, it is directly proportional to r square. Then we'll write terminal velocity of the big drop divided by terminal velocity of the small drop is equal to radius of the big drop divided by radius of the small drop whole square. What is the radius of the big drop? Capital R. And okay, here we have to substitute. They gave how many drops they have given? 8 drops they told. So in the place of this, we'll write as they told 8 drops, then R is equal to 8 whole power 1 by 3 into small r. So R is equal to 8 whole power 1 by 3, 8 cube whole power 1 by 3 into R. From this, R is equal to, these two get cancelled, 2R. Capital R is equal to 2R. Means radius of the big drop is equal to 2 times the radius of the small drop. Radius of the big drop will be equal to radius of the small drop. So terminal velocity of the big drop divided by terminal velocity of the small drop is equal to radius of the big drop is equal to what? 2r. Radius of the small drop is r whole square. Then r gets cancelled. Terminal velocity of the big drop divided by terminal velocity of the small drop is equal to 2 2s are 4 by 1. Terminal velocity of the big drop divided by terminal velocity of the small drop is equal to 4:1. Then what is given? Terminal velocity of the small drop is given. VTS is given. It is what? 10 centimeters per second. Then if you bring it to right side, terminal velocity of the big drop terminal velocity of the big drop is equal to 4 into terminal velocity of the small drop. Therefore, terminal velocity of the big drop is equal to 4 into terminal velocity of the small drop is 10 meters per second, 10 centimeters per second. So VTB is equal to 40 centimeters per second. A option is correct. 40 centimeters per second. Right. This is water is in steady flow of the along the horizontal pipe with non-uniform cross-sectional area at a point in the pipe where the area of cross-section is 10 centimeters square. The velocity of the water 1 meter per second square, and the pressure is 22,000 pascals. The pressure at another point where the cross-sectional area is 5 centimeters. Here one pipe is there. Water is flowing steadily, means what is streamline flow along the horizontal pipe with a non-uniform cross-sectional area. At a point in the pipe where the area of cross-section is 10 centimeters square, the velocity of the water is 1 meter per second and the pressure is 2000 pascals. The pressure at the point where the cross-sectional area is 5 centimeters. So according to this given data, they have given, according to this, they have given that a pipe is there which has a different area of cross sections. A pipe is there which has different area of cross sections. So first one is that a larger area of cross section. Then first one is that 10 centimeters square means what? Larger area of cross section. It is that a larger area of cross section, and the other one is that smaller area of cross section. The area of cross section at the first area of cross section at the first is A1 and it is taken as A2, A1 and A2. So then velocity at this end is given as 1 meter per second square. Velocity V is equal to 1 meter per second. Then what the velocity we don't know at the other end. First we have to calculate this. Pressure at the first end is given. Pressure at the first end is 1000 pascals. Pressure at the first end is 1000 pascals. Area of cross section A1 is given as a 10 centimeter square. 10 centimeters square. A2 is given as 5 centimeters square. This is the data. From this, we have to calculate first what is the velocity at the second cross-sectional area and pressure at the second cross-sectional area. These two we have to calculate. So to calculate the velocity at the second cross-sectional area, we will take the equation of continuity. A1 V1 is equal to A2 V2. A1 V1 is equal to A2 V2. So then whenever we want to calculate V2, V2 is equal to A1 V1 divided by A2. So therefore velocity at the second cross-sectional area. So V2 is equal to, what is A1? A1 is equal to 10 centimeters square. 10 centimeters. In the denominator also 5 centimeters is there. That's why I'm not converting. V1 is how much? 1 meter per second square divided by A2 is 5 centimeters square. So both in numerator and denominator, this will get cancelled 2 times. So velocity V2 is equal to 2 meters per second. Velocity we got 2 meters per second at the second cross-sectional area. Then from the Bernoulli's principle or Bernoulli's theorem, we'll write that P1 plus half rho V1 square, P1 plus half rho V1 square is equal to P2 plus half rho V2 square, P2 plus half rho V2 square. So then we have to calculate P2. For that, bring all this is to left side, right? And bringing it to left side, P2 is equal to P1 plus half rho we may take common 1/2 rho into V1 square minus V2 square. On substituting this, P2 is equal to P1. P1 is given how much? P1 is a 2000 pascals. 2000 plus 1/2 into rho is for the water. Density of the water, rho is equal to 1000 kg per meter cube. 1000 kg per meter cube. It is 1000. V1 square is 1 whole square. V2 square, 2 square. Therefore, pressure P2 is equal to 2000 m plus these two cancel in 1000 how many times? 500 times. 500 into 1 square is 1 and 2 square is taken as 4, right? Then pressure P2 is equal to 2000 plus 500 into minus 3. Therefore, pressure P2 is equal to 2000 minus 500. Therefore, pressure at the second cross-sectional area P2 is equal to 1500 pascals. This is 1500 pascals.
Sir,
Pascal.
minus 3, sir.
Oh, sorry. 1500. Sorry. 3 5s are 15. 500 I wrote. This is 3 5s are 15. 1500 pascals. Then it will be P2 is equal to 500 pascals. So it is. Okay. Then actually this is not the big chapter, but more formulas will be there from this chapter. All these are the previous case set problems. Next, three liquids of masses are taken in three identical cubes of cubical vessels A, B, C. Their densities are PA, PB, and PC respectively. If pressure of the A is less than that of pressure of B, less than that of the pressure of C, the force exerted by the liquid on the base of the vessel, whatever it may be, three liquids of equal masses, they told it, equal masses taken and the three identical. So if they are equal masses means force experienced will be same. Then three different liquids of masses taken, three identical cubes of cubical vessels ABC. Then as mass of A will be equal to mass of B and mass of C. If masses are same, then force experienced on them. Force is nothing but watch. It is the product of mass into acceleration due to gravity. So force experienced on the bottom will be FA is equal to FB is equal to FC. Forces experienced will be same for all of them. Same on all the three is a correct option. The same in all the options is correct. Next, two solid spheres, one of the steel and other one is aluminum, when immersed completely in water have equal weights. When the solid piece or weight in air is. So actually two solid pieces, one is the steel and other one is aluminum. aluminum weight is less. Aluminum weight is less when compared with that steel. Nothing but density is less for the aluminum and more for the steel. But whenever they have immersed in the liquid, both of them, they are showing the equal weights. They are showing that equal weight. That means in the air, if the aluminum piece have the more weight, then more weight than the steel, then it will show equal weight in the liquid. Actually, density of the steel is more than that of the density of the aluminum. So even though both the aluminum sphere and solid pieces, aluminum piece and steel piece, if they are immersed, both of them, they are showing that equal weights. So to show the equal weights, aluminum should have more weight in the air. Then it will show equal weight whenever dipped in the liquid along with that steel. A body weighs 50 grams in air and 40 grams in water. How much would it weight in a liquid of specific gravity 1.5? Specific gravity or relative density will say that. Specific gravity or relative density both will be same. Whenever we take that, weight of the body in air is 50 grams and weight of the body in water is given. Weight of the body in water is given 40 grams. Then specific gravity or relative density. So specific gravity or relative density, it is given as 1.5. Then we'll take that. Specific gravity or relative density is equal to. So weight of the body in air minus weight of the body in liquid divided by. So they asked to calculate what is the weight of that, how much weight in a liquid, what is that weight in a liquid, WL is to be calculated. So weight of the body in air minus weight of the body in liquid divided by weight of the body in air minus weight of the body in water will take. In water. From this we will take, it is a 1.5. Relative density is given as 1.5. Weight of the body in air is 50 grams minus weight of the body in liquid is to be calculated. So divided by weight of the body in water is 50. Weight of the body in air is 50. Weight of the water in weight of the body in the water is how much? Weight of the body, it's 40 grams. 40 grams in water. Then 35 is answer. So then 1.5 is equal to 50 minus WL divided by 40. 50 minus 40 will be equal to 10. So if you bring it to this side, 1.5 into 10 will be equal to 15. 15 is equal to 50 minus WL. Therefore, bring the WL to left side and 15 to right side. Therefore, we will get WL is equal to 50 minus 15. Therefore, WL is equal to 35 grams. WL is equal to 35 grams. This is WL is equal to 35 grams, right? Water rises in plant fibers due to capillarity. Capillarity means what? Rise of liquid. So many examples are there. In the wick, oil that rises, or in the water plants that water rises. Whenever we wipe our body or any surface, if it is wet, then it is due to the capillary. It will be dry. It becomes dry due to the capillarity action only. Like many applications are there for this capillarity action, right? Next one. See, the value of surface tension of the liquid at a critical temperature is value of surface tension at critical temperature. It will be 0. At the critical temperature, the value of surface tension will be 0. Next, the spherical shape of the raindrops is due to surface tension. Spherical shape of the raindrops is due to surface tension. Next, surface tension is due to cohesive forces between the molecules. The force of attraction between the similar kind of the molecules is called as the cohesive force. The surface tension is due to cohesive forces between the molecules. Adhesive force means the force of attraction among the different type of molecules is called as the adhesive force. Cohesive force means the force of attraction between the similar kind of the molecules. Okay, so I'm going to stop this chapter here, and I'll go for the next chapter, heat part. This is heat means thermal properties of matter, thermodynamics, and kinetic theory of gases. Heat. Combinedly, I am taking thermal properties of matter, thermodynamics, and kinetic theory of gases. See, first, if I take thermal properties of matter, we need the difference between the heat and the temperature. What is meant by heat? Heat is the sense of hotness or coldness of the body. The sense of hotness or coldness of the body is called as the heat. Heat is one form of the energy. Heat, it is measured in joules or calories. It is measured in joules or calories or calorie. We'll say the calorie. Then temperature. If you want to measure the heat, we will use the specific way is there to measure the temperature. Calorimeter. Calorimeter is there to measure the temperature. We will use the calorimeter. Then temperature. Temperature is nothing but measure of hotness or coldness of the body. For example, if you touch one object, we may feel its hotness or its coldness. So how much hotness it has or how much coldness it has, the measure is called as measure of hotness or coldness of the body is called as the temperature. The measure of hotness or coldness of a body is called as the temperature. So temperature, it is measured in degree centigrade, in Kelvin, or in Fahrenheit. This is measured with the help of these scales. Temperature, it is measured with the help of the Celsius scale, Fahrenheit scale, or Kelvin scale. So to measure the heat, we use the calorimeter, right? So then whenever we take different scales are there, how they have taken the different scales, it is based on the melting point and the boiling points. So melting point of the ice is taken as 0 degrees centigrade, and the boiling point of the water is taken as at 100 degrees centigrade. So lower fixed point they have taken as the melting point of the ice. Lower fixed point, we'll say that. And this is called as the upper fixed point. Upper fixed point is taken as the melting point of the boiling point of the water. So for all the scales, they have designed like this only. First one, if I take that Celsius scale, first scale is the Celsius scale. First one is the Celsius scale. This Celsius scale that consists of the Celsius scale that consists of total 100 divisions on it. Total 100 divisions on it. 0 degrees centigrade is the lower fixed point. 100 degrees centigrade is the upper fixed point. So temperature on this, if you want, C minus lower fixed point divided by total number of divisions on it. Then other scale is taken as the Fahrenheit scale. Fahrenheit. The spelling will be like this: Fahrenheit scale. Fahrenheit scale. This Fahrenheit scale that consists of total 180 divisions on it. Lower fixed point is taken as the melting point of ice, and the upper fixed point is taken as the boiling point of water. Total number of divisions on it is 180. Lower fixed point is taken as a 32 degree Fahrenheit, and upper fixed point is taken as a 212 degree Fahrenheit. This. So the temperature on this scale, if you want, F for temperature on the Fahrenheit scale, F for temperature on the Fahrenheit scale minus lower fixed point is 32 divided by number of divisions 180. This is the Fahrenheit scale. Third one is the Kelvin scale. Kelvin scale. Third one is that Kelvin scale. That Kelvin scale that consists of 100 divisions on it. It consists of 100 divisions on it. This is total number of divisions on it is 100. 273 kelvins is the lower fixed point, and 373 kelvins is the upper fixed point. Then temperature on it, if you take that K for temperature on the Kelvin scale, 273 is the lower fixed point. Total number of divisions are taken as 100. This is. So we can compare these with the Celsius scale, we can compare with that Fahrenheit scale, or Celsius scale we can compare with the Kelvin scale. Our Fahrenheit scale and the Kelvin scales we can compare. So first I am taking that I'm taking the comparison between the Celsius scale and the Fahrenheit scale. If I take the comparison between the Celsius scale and the Fahrenheit scale, C minus 0, nothing but C only. C divided by 100 is equal to F minus 32 divided by 180. F minus 32 divided by 180. So 0 and 0 gets cancelled. 5 2s are 10 and 9 2s are 18. There, if you want temperature on the Celsius scale, it will be equal to 5 by 9 into F minus 32. 5 by 9 into F minus 32. This is C is equal to 5 by 9 into F minus 32. This is the temperature on the Celsius scale. If you want temperature on the Fahrenheit scale also, we can measure. We can bring this 9. So this is a reversal. This is a 9 by 5C. 9 by 5C plus 32 is equal to temperature on the Fahrenheit scale. If you know temperature on the Fahrenheit scale, and if you want the temperature, if you want to calculate temperature on the Celsius scale, this is the formula. If you know the temperature on the Celsius scale, and if you want to measure the temperature on the Fahrenheit scale, the second one is the formula, right? So we can take that at minus 40 degrees, temperature on the Celsius scale will be equal to temperature on the Fahrenheit scale. At minus 40 degrees, temperature on the Celsius scale, TCL, right? Capital T. So temperature on the Celsius scale will be equal to temperature on the Fahrenheit scale. Okay. So if I compare the temperatures of this Celsius scale and Kelvin scale. Celsius scale and Kelvin scales I am comparing. What is this? C minus 0, nothing but C only. C by 100. C by 100 is equal to K minus 273 divided by 100. 273 divided by 100. So 100 and 100 gets cancelled. So C is equal to K minus 273. Then temperature on the Celsius scale, this is temperature on the Kelvin scale, right? So temperature on the Kelvin scale, if you want, that will be equal to temperature on the Celsius scale plus 273. Let us suppose temperature on the Celsius scale is 27 degrees centigrade. Then the temperature on the Kelvin scale is 27 plus 273. So temperature on the Kelvin scale is 300 kelvins. Temperature on the Kelvin scale is 300 kelvins. This is the relations. We can compare that Fahrenheit scale as well as the Kelvin scale. So temperature on the Fahrenheit scale, temperature on the Fahrenheit scale, and temperature on the Kelvin scale will be same at 574.6 degrees. At 574.6 degrees, this Kelvin scale temperature and temperature on the Fahrenheit scale will be same. Both the temperatures will be same on Kelvin scale as well as the Fahrenheit scale, right? Next, so whenever we take that gas laws are there or expansions. So linear expansion, if I take that linear expansion, let us suppose one rod of length L is there. It is a rod whose length is taken as L1. L1. On heating, the length of the rod is increased. On heating, length of the rod is increased. That is taken as L2. L2 is the length of the rod. So linear expansion, this is alpha is called as the linear expansion coefficient. So the temperature is taken as a T1. The temperature is taken as a T2. T1, T2 are the temperatures. T1, T2 are the temperature. So L is linear expansion coefficient. Alpha is equal to L2 minus L1 divided by L1 into T2 minus T1. T2 minus T1. This is the formula to calculate linear expansion coefficient. This is called linear expansion coefficient or coefficient of the linear expansion. Second one is called as the areal expansion. This is areal expansion. This is the area of one plate. Let us suppose A1 is the area of this plate. A1 is the area of the plate at temperature T1. On increasing the temperature, the area of the plate that is increased. So on increasing the temperature, area of the plate is increased to a temperature T2. Then area of this one is taken as A2. Then areal expansion coefficient is taken as a beta. Beta is equal to A2 minus A1 divided by A1 into, here I have to take L1. A1 into A2 minus A1 by A1 into T2 minus T1. What is the unit per degree centigrade? For this also we'll take that per degree centigrade. Per degree centigrade is that. Next, whenever I take that cubical expansion or volume expansion. Areal expansion means cubical or volume. Volume expansion. Volume expansion. Coefficient of the volume expansion gamma is equal to volume V2 minus V1 divided by V1 into T2 minus T1. T2 minus T1. This is the volume, 1 cube if I take. If I take it's a cube. Volume of the cube is taken as a V1. V1 is the volume of the cube. This is increased to a volume V2. Then V1 is that initial volume at temperature T1 and V2 is the volume at temperature T2. This is called as the areal volume expansion coefficient. The relation between all the areal expansion, linear expansion, and cubical expansions, if you take alpha is to beta is to gamma, alpha is to beta is to gamma is equal to 1 is to 2 is to 3. 1 is to 2 is to 3. Then alpha is equal to alpha by 1 is equal to beta by 2 is equal to gamma by 3. Like this we'll write. So alpha by 1 is equal to beta by 2 is equal to gamma divided by 3. So if we want the relation between these two, how to take that? Beta is equal to alpha. If you want this one and this one, gamma is equal to 3 alpha. Then unequating. From this what we'll write? Beta is equal to 2 alpha and gamma is equal to 3 alpha. Or gamma we may write it as gamma is equal to alpha plus beta also we may write. Because 3 alpha is equal to alpha plus 2 alpha. Therefore gamma is equal to alpha plus beta also we may write. Next, gas laws. Gas laws. What are the gas laws? First one is the Boyle's law, Charles' law, Gay-Lussac's law, Graham's law. These are Dalton's law of partial pressures. So these are the gas laws. The basic laws means one is the Boyle's law. Boyle's law states that at constant temperature, the pressure of the given mass of the gas is inversely proportional to its volume. At constant temperature, the pressure of the given mass of the gas is inversely proportional to its volume. That means if volume increases, then pressure decreases. If volume decreases, pressure will be increased. So if you take the pressure on the y-axis, pressure is taken on the y-axis and volume is taken along the x-axis. Pressure is on the y-axis and volume is taken along the x-axis. So from there we'll write with increasing of the volume, pressure that decreases. This is the shape of the graph. Next, Charles' law at constant pressure, Charles' law at constant volume. Second one is Charles' law. Charles' law at constant pressure. Charles' law at constant pressure. So then, according to this, the volume of the given mass of the gas is directly proportional to absolute temperature. If you plot the graph between the volume and temperature, with increasing of volume, with increasing of temperature, volume also increases. This is taken as temperature and volume. With increasing of temperature, volume also increases. Third one is Charles' law. At Charles' law at constant volume. Charles' law at constant volume. Then according to Charles' law at constant volume, the pressure of the given mass of the gas is directly proportional to absolute temperature. Then if I plot the graph like this, with increasing of temperature, pressure also increases. So pressure is taken or temperature is taken like this, and pressure is taken like this. With increasing of temperature, pressure also increases. This is the graph. Okay, Charles' law, Boyle's law. These are next. Triple point. Triple point. It is a common point for the coexistence of matter. Triple point is the common point for the coexistence of the matter. So whenever we take three This is the triple point means what? Solid, liquid, and gas. Solid, liquid, and gas. So whenever we melt that solid, it becomes as liquid. On increasing temperature of the liquid, it becomes on increasing the temperature of the liquid, it becomes as a gas. So each and every point on this line, it will say, it will give that coexistence of the matter. This line is called as the fusion line. It is. This is called as the fusion line, and this line is called as the vaporization line. This is called as vaporization line, and this is called as the sublimation line. Sublimation line. This is the common point for the coexistence of matter. Solid becomes liquid, solid becomes liquid, liquid becomes gas, or gas that becomes gas that again that cools down and comes to liquid. Actually, it is a common point for all the three. At this triple point, they have defined all: absolute temperature, pressure at normal atmospheric pressure, and all those they have defined at the triple point only. Fine. This is some of the substances, they'll have only solid and liquid states. For example, wax, if you take candle wax, so on heating, it becomes solid to liquid. Again, on cooling, it becomes solid. You don't get that vapor state, gaseous state. That is only two states. Like other one is there, without on heating, without getting the liquid state, directly it comes from solid to gas, it will come. That is called as the sublimation. The process of converting from solid to gas directly is called as the sublimation. Solid iodine will do this. So solid iodine will do this. That is called as the sublimation. The process of attaining directly gaseous state from the solid state without getting the liquid state is called as the sublimation. Is called as the sublimation. Next, when we take that specific heat, it is the amount of the heat required to it is the amount of the heat required to increase the temperature of the unit mass of the substance by 1 degree. Let us suppose it is the substance. I want to increase its temperature by 1 degree centigrade. To increase this temperature, I have to supply certain amount of the heat. dQ is the amount of the heat I have to supply to it. Then 1 degree I have to increase. 1 degree centigrade or 1 Kelvin I have to increase. Then how much heat is needed to increase 1 degree centigrade or 1 Kelvin of unit mass of the substance? How much heat is needed? That is called as the specific heat. It is the amount of the heat required to raise the unit mass of the substance by 1 degree or 1 Kelvin is called as the specific heat. So Q is proportional to M into delta theta or M into theta. M into delta theta is to write. So it depends upon that mass of the substance and temperature difference through which we are increasing. So Q is equal to MS into delta theta, where S is called as the specific heat. Therefore, specific heat S is equal to Q divided by M into delta theta. The unit of this specific heat, if you take joule per kg per Kelvin or calorie per gram per degree centigrade. Calorie per gram per degree centigrade or joule per kg per Kelvin. This is the specific heat. It is the amount of the heat required to raise the unit mass of the substance through 1 degree centigrade or 1 Kelvin is called as the specific heat. So next one is that latent heat. What is that latent heat? It is the amount of the heat required to convert the state. So latent heat. Latent heat is the amount of the heat required to increase the, means to turn or to convert from solid to liquid or liquid to vapor, like that. So latent heat is the amount of the heat required to convert the state of matter. So there are two types of the latent heats. Latent heat of fusion. Latent heat of fusion. Then latent heat of vaporization, latent heat of fusion, and latent heat of vaporization. This is to melt ice to liquid. Means what? Ice to water if you want melt. Then amount of the heat to convert the ice into water, how much it is needed, this is called as a latent heat of fusion. This latent heat of fusion, latent heat of fusion is latent heat of fusion of ice is taken as 80 calorie per gram. So this latent heat formula, Q is proportional to M, or Q is equal to L into M. Q is equal to L into M. L is equal to Q divided by M. The unit of the latent heat is joule per kg or calorie per gram. Joule per kg or calorie per gram. Then latent heat of ice is 80 calorie per gram. Or if you take this 3.36 into 10 power 6 joule per kg. Or if you take this latent heat of vaporization, we have to convert from the water to vapor. Water to vapor, we have to turn it. So then amount of the heat required to change the state of substance from liquid to vapor, the heat required is called as the latent heat of steam. Latent heat of the steam is equal to 540 calorie per gram. 540 calorie per gram, or 2.25 into 10 power 5 joule per Kelvin. 2.25 into 10 power sorry, reverse it is 2. Reverse it is 5. This is a 3.35 into 10 power 6, and this is a 5 not, it is 6. This is a 2.26 into 10 power 6 joule per Kelvin. This is 3.35 into 10 power 5, 3.35 Kelvin, 2.26 into 10 power 6 joule per Kelvin it is. This is latent heat of fusion of ice and vaporization of water. So we'll see the numericals from this chapter tomorrow, and we'll complete that remaining concept also in the regarding this tomorrow in the tomorrow's class. Thank you.
Thank you, sir.
Thank you, sir.